What is the moment of inertia of a wheel shaped like a ring, which has a radius of 34 centimeters? 34 centimeters would be 0.34 meters, and a mass of 4.5 kilograms. We're looking for the moment of inertia or rotational inertia, and since this is a ring, the formula is I equals mr squared. If I is equal to mr squared, I will be equal to 4.5 times 0.34 squared. The 0.34 being squared because the radius is squared in the formula. When you take 4.5 and you multiply by 0.34 squared, you get 0.52 kilograms meters squared. For the units, we're just taking the quantities that we're multiplying and using their units. Nothing to memorize, just using what you're used to. What is the moment of inertia of a 2.5 kilogram solid sphere which has a radius of 6 centimeters? The mass is 2.5 kilograms. The radius would be 0.06 meters. Watch those units. We don't use centimeters, we use meters. Because this is a solid sphere, the moment of inertia, or the rotational inertia, would be equal to 2/5, 2 over 5, mass radius squared. I equals 2/5 times 2.5 times 0.06 squared. Put that into our calculator. We should get 3.6 times 10 to the negative third power kilograms meters squared. If we put it in scientific notation, if we leave it in the default format, we would get something like 0.0036 kilogram meter squared. Number 3, what is the moment of inertia of a disk which has a mass of 4.4 kilograms and a radius of 45 centimeters? The mass is 4.4 kilograms. The radius is 0.45 meters. Keeping with our guess method, we're continually writing out our given so we can see exactly what we have and what we need. Because this is a disk, our rotational inertia, moment of inertia, is 1/2 mr squared. I equals 1/2 times the mass of 4.4 times the radius of 0.45, which will be squared. As you're doing this, don't forget your guess method. Write the given out. It makes it much easier to answer these. When we put this into our calculator, we should get something close to, or right about at, 0.45 kilogram meters squared. The Earth has a mass of 5.98 times 10 to the 24th kilograms. Let's go ahead and write that. Mass equals 5.98 times 10 to the 24th kilograms. Average radius of 6.37 times 10 to the 6 meters. So R equals 6.37 times 10 to the 6 meters. Assuming that the Earth is a sphere, what's the moment of inertia for the Earth that runs from the North Pole to South Pole? No one cares about that, but pretty much what's the moment of inertia? Since this is a sphere, again, we have I is equal to 2/5 mr squared. They gave us the mass of 5.98 times 10 to the 24th. And they gave us the radius at 6.37 times 10 to the 6. We've summarized that in the margins, making it much easier for us. In our calculator, we will take 2/5 times the mass of 5.98 times 10 to the 24th times the radius. Here I would say times open parentheses 6.37, either times 10 to the 6th power or that second EE6, close parentheses, and then square it. That way you're squaring the radius and not squaring the entire problem, or squaring the power of 10. Once you get that all in your calculator, you should get 9.71 times 10 to the 37th power kilogram meter squared. Number 5, a torque of 100 Newton meters, so torque T is equal to 100 Newton meters, is applied to a sphere. So keep in mind we're working with a sphere initially at rest. That means omega naught is 0, which has a moment of inertia, so I, of 400 kilogram meters square. Kind of just summarizing things in the margin makes things much, much easier. Torque is 100, omega naught is 0, I is 400. What is the resulting angular acceleration of a sphere? What is it asking us for? Alpha. Okay, well, what do we have? We have torque, we have omega naught, and we have rotational inertia. Where does alpha fit into that? If we remember that torque is equal to I alpha, rearrange, we would say alpha is torque over I, or torque over rotational inertia, T over I. So we'd have 100 over 400. And 100 divided by 400 would be 0.25. Alpha, the units would be radians over second square. Radians per second square. B, what is the angular displacement? What is it asking us for? Angular displacement? Theta, yes. After 9 seconds. So we have a new parameter. Time is 9 seconds. And we're looking for theta. According to the information I have omega naught, I have alpha, I have time, and I'm looking for theta. I'm going to use the equation, the rotational kinematic equation of theta is equal to omega naught times time plus 1/2 alpha time squared. Omega naught is 0, so omega naught t goes away because 0 times anything is still 0. We're left with 1/2 times alpha times time squared. So 1/2 times 0.25, which is the answer we got in A, times 9 seconds squared, or 81. 1/2 times 0.25 times 81 should get us something around 10.13 radians, because theta is measured in radians. 10.13 radians. Number 6, a force of 80 newtons, so let's go ahead and mark down force equals 80 newtons, is tangentially applied to the outer edge of a wheel approximated as a solid disc with a radius of 30 centimeters. So our radius is 0.3 meters. And we'll keep in mind that this is a disc. How much torque is being applied? Let's see if we can get this to write in properly. 0.3 meters. How much torque is applied? Well, how do we calculate torque? Well, we said earlier torque is I alpha. That doesn't do us any good here. If we look through our notes, thumb through, we find another formula, force times radius. The force is 80. The radius is 0.3. 80 times 0.3 is 24, and the unit would be newtons times meters, or Newton meters. So 24 Newton meters. B, if the angular acceleration of the wheel is 3.4, so alpha is 3.4 radians per second square, what is the mass? Well, we need a formula that we can get mass into. We have torque. We just solved for torque. They've given us alpha. Well, if we use torque is equal to I alpha, we can break I into its components, knowing that it's a disk would be torque is equal to I alpha. I, rotational inertia, would be 1/2 mr squared, right? So torque is equal to 1/2 mr squared times alpha. Now we've got some variables that we can use. That guess method is helping us all along the way. We said torque was 24. 24 would then be equal to 1/2 times the mass times 0.3 squared times 3.4. And we get 156.9 kilograms for our mass. Just watch your algebra 24. You're going to multiply the 2 over, divide by the 0.3 squared over, divide by the 3.4, and you get the 156.9 kilograms for the mass. Hey, we're halfway there. We're on the back side. Torque of 30 Newton meters, so T equals 30 Newton meters, is tangentially applied to a ring which has a moment of inertia of 2.81 kilogram meters squared. What will be the resulting angular acceleration of this ring? Well, we have the torque, we have the rotational inertia. Don't forget T is equal to I alpha. So we have 30 is equal to 2.81 times alpha. 30 divided by 2.81. 30 divided by 2.81 will get us about 10.68 radians per second square. If the ring started at rest, so omega naught is 0, what is the angular velocity after 5 seconds? So omega naught being 0, time is 5. Alpha we just solved at 10.68. We're looking for our omega. Omega is equal to omega naught plus alpha times time. Omega naught is 0, that just kind of goes away. And we're left with alpha 10.68 times time of 5. So that's my omega naught going away. I've just marked it as 0 and just taking it out because 0 plus anything doesn't change anything. We have 10.68 times 5. And when we do the math, we get omega should be about 53.4 radians per second. Consider a wheel which is shaped like a ring. Okay, so we have that it's a ring. Has a mass of 8.2 kilograms. So let's go ahead and record our mass at 8.2 kilograms and a diameter of 74 centimeters. All right, diameter 74 centimeters means the radius is 37 centimeters. We need this in meters. 37 centimeters would be 0.37 meters. Tangential force of 50 newtons. So we've got force is equal to 50 newtons. Applied to the outer edge of the wheel for 5 seconds, so time equals 5 seconds. The wheel is initially at rest. Omega naught would be 0 radians per second because omega naught would be the initial angular velocity. And because this is a ring, we know our formula I equals mr squared if we need that. What is the magnitude of the torque being applied to the wheel? Well, torque is I alpha. I haven't solved for I, haven't solved for alpha. But torque is also force times radius. Well, I have the force at 50 and the radius at 0.37. So 50 times 0.37, put that in my calculator. I get 18.5 Newton meters. What is the moment of inertia of this wheel? Moment of inertia, we said that, yeah, they're calling it a wheel here, but a wheel is like a ring, and they told us that it was a ring. I equals mr squared. Mass is 8.2. R is 0.37. That's the radius in meters. So 8.2 times 0.37 squared. We put that into our calculator, and we should get about 1.12 kilograms meters squared. C. What will be the resultant angular acceleration? Well, remember we've done an angular acceleration a little bit today, and alpha is equal to torque over rotational inertia. Because T is I alpha, we rearrange and we say alpha then would be T over I. We've solved for T in the 8A and got 18.5. And then we just solved for I in 8B and got 1.12. So 18.5 divided by 1.12 should get us about 16.52. Since this is alpha, our units should be radians per second squared. D. What will be the angular velocity? What is angular velocity again? Omega, right? Yeah, omega. Will be the angular velocity of the wheel after 5 seconds. So our time is still 5 seconds. We're looking for omega. We know omega naught is 0. We know alpha is 16.52 and the time is 5. So that omega naught goes away. It's 0. So 16.52 times 5 will get us our omega. Put that in our calculator, we get 82.6 radians per second. Again, summarize your work. Show the given off on the side. It makes things so much easier when you have one place to look where it's all summarized. Going to E, the final one in this question. What will be the total angular displacement? Angular displacement is theta of this wheel during the 5-second interval. Well, if we have omega naught 0, time is 5 seconds. We've solved for alpha. We can use theta is equal to omega naught t plus 1/2 alpha t squared. Omega naught t is 0. It's gone. We're left with 1/2 times alpha, 16.52, which we solve for in 8c, times time squared, which would be 5 squared, or 25. 1/2 times 16.52 times 25 should get us 206.5 radians, the unit of theta. A ring and a disk of equal mass and radius are on the top of a hill. If both race down to the bottom, which will finish first? Use any equations that you need and explain how the equations support your conclusion. So I've got a ring on the left and then a disk, so I've got a visual representation. They said they're the same mass, so I'll just say, okay, well, each one has a mass of m. They have the same radius, so they'll both have a radius of r. Now, the difference between them that we've been learning so far is the rotational inertia and how you calculate that. The ring's rotational inertia is I equals mr squared. For the disk, the rotational inertia would be I equals 1/2 mr squared. Now let's just keep in mind what this means. I, the moment of inertia or rotational inertia, is the object's tendency to resist angular acceleration. It's the sluggishness. It's an object at rest that wants to stay at rest. The larger the I, the more it's going to resist that change. What is that change? An acceleration. So if you don't resist acceleration, you'll speed up very quickly. If you resist acceleration, it's going to take longer for you to get up to speed. So a larger I will have more resistance. A smaller I will have less resistance and will have a higher propensity to speed up. So the disk has a smaller I. It's 1/2 of mr squared instead of mr squared. The disk has a lower moment of inertia. It will accelerate faster, and since it accelerates faster, it will reach the bottom of the hill first.